We now move on to the Bronze Age. So around 3000 BC, people in the mountainous area of Israel near the Dead Sea had found a means of producing harder materials from copper. Objects such as crowns and mace heads have been discovered. They are made from an alloy of copper and arsenic, which is harder than the pure copper. In ancient times, bronze was an alloy of copper and arsenic. The ores in which copper minerals are found are often contaminated with other metals, such as arsenic, lead, nickel, and bismuth. Lead contaminants soften the copper, but arsenic contaminants produce a harder, finer product which is more readily worked and cast. Thus, arsenic bronzes became favoured over pure copper. By 3000 BC, it was discovered that tin produced the best alloy with copper. Tin bronzes are harder and less brittle than arsenic bronzes. The tin alloy could be more readily shaped and sharpened, and so cutting tools and weapons of war could be made from it. Kings and emperors demanded bronze for their palaces and tombs. Tin ores do not occur in the Middle East, and so they had to be obtained from Europe and Armenia. An extensive trade network developed with Europe by 2000 BC. And you can see on this map the areas in the orangey brown are the areas where the bronze trade took place. So European contact with the metalsmith of the Middle East led to the development of this technology in many European countries, including Spain around 1800 BC. By 800 BC, vast copper deposits were being mined in Austria, and this copper was turned into bronze by the European bronzesmiths.
They've evened a metal sword in a couple of minutes.
The Iron Age was next to come about. So unlike copper, which could be easily smelted, cast and shaped, iron required a much higher temperature to smelt it from its ores. Iron was not as malleable unless it was red hot, and impurities were often difficult to remove. Native iron is also much rarer than native copper. The major sources of native iron were the few meteorites which strike the Earth from space. The Sumerians called this meteoric iron heaven metal, and it was prized more than gold. Early iron weapons were made by chipping off fragments of iron from meteorites. This type of iron was resistant to rusting because of its nickel content. The Iron Age probably began in the Hittite Empire of the Middle East between 1500 and 1200 BC. Smelted iron became a vital part of their culture. An important iron working site existed in northeastern Iran in about 1200 BC. Iron bracelets, pins, buckles, nails, knives, and sickle blades have been discovered in archaeological digs. The blacksmiths had discovered how to convert iron into steel. The iron was heated at high temperatures with charcoal and then suddenly quenched in cold water. The process incorporated carbon into the iron to produce steel. Steel can be made with a keen cutting edge, which made it ideal for weapons such as swords. The strength of steel made it useful for machines and structural purposes. The earliest known iron smelter which still remains in existence operated in the Austrian Alps in about 500 BC. Crushed iron ore and charcoal were mixed and smelted. Air from blowpipes and bellows fanned the fire. The iron which emerged was in the form of a black, spongy mass. If the iron was exposed to too much carbon, it became hard and brittle due to the formation of cementite. Similar furnaces must also have operated in the Middle East, and iron began to be traded to Egypt and Syria. To be useful, the iron needed to be hammered at red hot in order to squeeze out the slag and solid impurities, as well as burn off most of the carbon. Heating the iron produces iron oxide, and as the hot iron is beaten and folded thousands of times at the forge, this iron oxide reacts with cementite crystals to produce pure iron. This was the job of the blacksmith, and a task that is still performed today. So by 100 BC, strips of iron were being used for chariot wheels and barrel hoops. And here you can see some iron that was used to make armour, and you can see the rust that's occurred over time. So let's now have a look at how we convert iron into steel.
Few fireworks displays are more spectacular than the drama that is steelmaking. The story of hot metal and cold steel is fascinating from start to finish, especially when seen through the experienced eyes of United States Steel. For our company, the story begins with a blast. As rock explodes and the raw materials of steel are tossed from the earth. The rock is taconite, and the prize inside is crude iron ore. We get at it by grinding the rock to powder and separating the ore with powerful magnets. Then we form and heat the ore into marble-sized pellets that will later be converted to iron. From bituminous coal, we create coke to fuel the iron-making furnaces. We crush the coal, seal it in airtight ovens, bake for 12 to 16 hours, and remove it from the oven as solid carbon fuel. The fuel and pellets come together in the blast furnace, where we add just enough limestone to remove impurities. From below, a continuous blast of superheated air combusts the coke, intensifying the heat and changing raw materials into molten iron. Sometimes more than 9,000 tons of it a day in our largest blast furnace, where it reaches a temperature of 2,700 degrees Fahrenheit. At regular intervals, we tap this blistering brew into giant submarine ladles that ride on rails to the basic oxygen shaft, where iron will be turned into steel. In this fast-paced sequence, up to 250 tons of steel can be made to order in less than 45 minutes. We begin the steel-making process by dumping recycled steel scrap into the basic oxygen furnace and adding hot iron. Sparks steal the show when high-purity oxygen is blown into the mix at supersonic speeds and molten iron becomes molten steel. Now we're ready to create the custom blends that make steel the most widely used metal on the planet. In fact, we produce over 1,500 different chemistries to meet customer demand for cutting-edge, value-added steel. Look for another show of sparks as we tap molten steel from the Bop vessel into a ladle. Then, for most of our steels, it's on to the vacuum degasser, where they are made highly formable. The focus then shifts to forming and finishing, which determine even more of the steel's characteristics. The first step in this sequence is to position the ladle above a massive tundish or funnel that feeds a continuous caster containing molds that shape the steel. The molten steel, now at 3,000 degrees Fahrenheit, is channeled from ladle to tundish to caster, where it cools to a red-hot solid. The shape of the mold determines the shape of the semi-finished products that come out of the caster. And since most U.S. steel plants make sheet products, most of our casters output slabs, typically 8 to 9 inches thick and 3 to 5 feet wide. As they exit the caster, slabs are cut into sections up to 40 feet long and stacked to await further processing. Then it's on to the hot strip mill. This is where we begin transforming steel slab into steel sheet. Slabs are reheated to 2,400 degrees Fahrenheit and descaled before running through a series of roughing stands that make them thinner and longer. Then they cycle through finishing stands where they are rolled even thinner. Finally, they are cooled and rolled into coils that may be thousands of feet long but only fractions of an inch thick. A far cry from the chunky rectangle that came out of the caster. And the entire process is untouched by human hands, controlled instead by operators using state-of-the-art automated equipment in pulpits that overlook the action. Next, we move to the pickle line, where coils move through an acid bath that cleans the surface. Some of the emerging coils are shipped directly to customers as hot band. Others are destined for applications that require special finishing, beginning with cold rolling to make them even thinner. At that point, coils may be shipped or go on to one or more additional finishing processes. Coating to make the steel resistant to corrosion. Tinning to further reduce the gauge and add the tin coat we commonly see on canned goods. Annealing to make steel that is easier to bend and form. And tempering that uses special rollers to add hardness and create surface textures and other special finishes. In fact, many of our products leave the finishing facilities as the industry's newest superstars. Lighter, stronger, highly engineered, formable steels that were unheard of just a few short years ago. No wonder the story of steelmaking stays so fresh.
So the modern era has seen no dramatic movement away from iron. Even today, iron is still the most widely used metal. In the last 100 to 150 years, aluminium and titanium have also added to the list of metals that we use today. In the next video, you will be working through making a timeline, using dates to show when metals were used in history, and answering some revision questions. Please enjoy.